일론머스크가 2월 5일 드워케시 팟캐스트에서 폭탄 발언을 했습니다. 36개월 안에 AI를 돌리기에 가장 싼 곳이 우주가 된다는 건데요. 지상에서는 허가 문제에 전력 부족까지 데이터센터 확장이 사실상 막혀 있다는 겁니다. 우주에서는 태양광 효율이 5배, 배터리까지 빼면 10배나 싸다는 계산이죠. 테슬라 자체 칩부터 달의 매스 드라이버까지 핵심만 추려서 들려드리겠습니다.
You're famously a big fan of solar. 1 terawatt of solar power, so with a 25% capacity factor, like 4 terawatts of solar panels, it's like 1% of the land area of the United States. And that's like we're in the singularity when we've got 1 terawatt of data centers, right? So what are we running out of exactly?
How far into the singularity are you, though?
You tell me.
Yeah, exactly. So I think we'll find we're in the singularity and like, oh, okay, we're still got a long way to go.
But is the plan to like put it in the space after we've covered Nevada and solar panels?
I think it's pretty hard to cover Nevada and solar panels. You have to get like permits from like the permits for that. Try getting the permits for that.
So the space is really it's really a regulatory play. It's like harder to build on land than it is in space.
It's harder to scale on the ground than it is to scale in space, but also you're going to get about 5 times the effectiveness of solar panels in space versus the ground, and you don't need batteries. I almost wore my other shirt, which says "It's always sunny in space," which it is. So, because you don't have a day-night cycle or seasonality, clouds, or an atmosphere in space, because the atmosphere alone results in about a 30% loss of energy. So you can, for any given solar panels can do about 5 times more power in space than on the ground, and you avoid the cost of having batteries to carry you through the night. So it's actually much cheaper to do in space. And my prediction is that it will be by far the cheapest place to put AI will be space in 36 months. Both SpaceX and Tesla are building towards 100 gigawatts a year of solar cell production.
How low down the stack, like from polysilicon up to the wafer to the final panel?
I think you got to do the whole thing from raw materials to finish the cell. Now, if it's going to space, it's actually it costs less and it's easier to make solar cells that go to space because they don't need glass, or they don't need much glass, and they don't need heavy framing because they don't have to survive weather events. There's no weather in space. So it's actually a cheaper solar cell that goes to space than the one on the ground.
Is there a path to getting them as cheap as you need in the next 36 months?
Solar cells are already very cheap. They're like farcically cheap. It's and if you say, I think like solar cells in China are around like 25-30 cents a watt or something like that. It's absurdly cheap, and when you take into account now put it in space and it's 5 times cheaper because it's 5 times. In fact, it's not 5 times cheaper. It's 10 times cheaper because you don't need any batteries. So the moment your cost of access to space becomes low, by far the cheapest and most scalable way to generate tokens is space. It's not even close. It'll be an order of magnitude easier to scale, and chips aside, an order of magnitude. Well, if the point is you won't be able to scale on the ground, it's just you just won't. People are going to hit the wall big time on power generation. They already are. The number of sort of miracles in series that the XAI team had to accomplish in order to get a gigawatt of power online was crazy. We had to gang together a whole bunch of turbines, and then we had permit issues in Tennessee and had to go across the border to Mississippi, which is fortunately only a few miles away. But then we still had to run the high power lines a few miles and build the power plant in Mississippi, and it was very difficult to build that. And people don't understand like how much electricity do you actually need at the generation level in order to power a data center? Because they look at the news will look at the power consumption of say a GB300 and multiply that by a thing and then think that's the amount of power you need.
All the cooling and everything.
Wake up, yeah. This is like that's a total noob. You've never done any hardware in your life before. besides the GB300, you've got to power all of the networking hardware. There's a whole bunch of CPU and storage stuff that's happening. You've got to size for your peak cooling requirements. So that means, can you cool even on the worst hours, the worst day of the year? Well, it gets pretty freaking hot in Memphis. So you're going to have like a 40% increase on your power just for cooling. Assuming you don't want your data center to turn off on hot days and you want it to keep going. Then you've got to say, well, there's another multiplicative element on top of that, which is, are you assuming that you never have any hiccups in your power generation? Like, oh, well, actually, sometimes we have to take the generators, some of the power offline in order to service it. Oh, okay. Now you add another 20-25% multiplier on that, because you've got to assume that you've got to take power offline to service it. So the actual roughly every 110,000 GB300s, inclusive of networking, CPU storage, cooling, margin for servicing power, is roughly 300 megawatts.
So, as you know better than anybody else, the total cost of ownership of a data center, only 10 to 15% is energy. And that's the part you're presumably saving by moving this into space. Most of it's the GPUs. If they're in space, it's harder to service them, or you can't service them. And so the depreciation cycle goes down on them. So it's just way more expensive to have the GPUs in space, presumably. What's the reason to put them in space?
Well, the availability of energy is the issue. If you look at electrical output outside of China, everywhere outside of China, it's more or less flat. It's very, maybe a slight increase, but for pretty close to flat. China has a rapid increase in electrical output. But if you're putting data centers anywhere except China, where are you going to get your electricity? Especially as you scale. The output of chips is growing pretty much exponentially, but the output of electricity is flat. So how are you going to turn the chips on? Magical power sources? Magical electricity fairies?
It sounds like you think the sort of like the process technology, like these 10,000 PhDs in Taiwan who know exactly what gas goes in the plasma chamber and what settings to put on a tool. You can just like delete those parts of those steps. Like fundamentally, it's get the clean room, get the tools, and figure it out.
I don't think it's PhDs. It's mostly people with who are not PhDs. Most engineering is done by people who don't have PhDs. Do you guys have PhDs?
No.
Okay.
We also haven't successfully built any fabs, so you shouldn't be coming to us for your fab advice.
I don't think you need a PhD for the stuff. So, but you do need competent personnel. So I don't know. I mean, like right now, if say like Tesla's pedal to the metal max production of going as fast as possible to get AI5, Tesla AI5 chip design into production and then reaching scale. That'll probably happen, around the second quarter-ish of next year, hopefully. And then AI6 would hopefully follow less than a year later. And we've secured all the chip fab production that we can.
Yes. But you're currently limited on TSMC fab capacity.
Yeah. And we'll be using TSMC Taiwan, Samsung Korea, TSMC Arizona, Samsung Texas, and we still
You've booked out all the capacity you can.
Yes, and then if I ask TSMC or Samsung, okay, what's the time frame to get to volume production? The point is not you've got to build the fab, and you've got to start production, then you've got to climb the yield curve and reach volume production at high yield. That from start to finish is a 5-year period. And so the limiting factor is chips.
Yeah.
Like limiting factor once you can get to space is chips, but the limiting factor before you can get to space will be power.
Why don't you do the Jensen thing and just prepay TSMC to build more fabs for you?
I've already told them that.
But they won't take your money? Like, what's going on?
They're building fabs as fast. No. They're building fabs as fast as they can. And so is Samsung. They're pedal to the metal. I mean, they're going, balls to the wall, as fast as they can. So still not fast enough. I mean, like I said, there will be I think if you say, I think towards the end of this year, I think probably chip production will outpace the ability to turn chips on. But once you can get to space and unlock the power constraint, and you can now do hundreds of gigawatts per year of power in space. Again, bearing in mind that average power usage in the U.S. is 500 gigawatts. So if you're launching, say, 200 gigawatts a year to space, you're sort of lapping the U.S. every 2.5 years. All U.S. electricity production. This is a very huge amount. But between now and then, the constraint for server side compute, concentrated compute, will be electricity. My guess is that we start hitting people start getting to the point where they can't turn the chips on for large clusters towards the end of this year. The chips are going to be piling up and won't be able to be turned on. Now for edge compute, it's a different story. So for Tesla, the AI5 chip is going into our Optimus robot, optimistic, and so if you have an AI edge compute, that's distributed power. Now the power is distributed over a large area. It's not concentrated, and if you can charge at night, you can actually use the grid much more effectively, because the actual peak power production in the U.S. is over 1,000 gigawatts, but the average power usage, because the day-night cycle, is 500. So if you can charge at night, there's an incremental 500 gigawatts that you can generate, at night. So that's why Tesla for edge compute is not constrained, and we can make a lot of chips to make very large number of robots and cars. But if you try to concentrate that compute, you're going to have a lot of trouble turning it on.
What I find remarkable about the SpaceX business is the end goal is to get to Mars, but you keep finding ways on the way there to keep generating incremental revenue to get to the next stage and the next stage. So the Falcon 9 is Starlink, and now for Starship, it's going to be potentially orbital data centers. But you find these sort of infinitely elastic, sort of marginal use cases of your next rocket and your next rocket and next scale up.
You can see how this might seem like a simulation to me. Or am I someone's avatar in a video game or something? Because it's like what are the odds that all these crazy things would be happening? I mean, rockets and chips and robots and space, solar power, and not to mention the mass driver on the moon. I really want to see that. You can imagine some mass driver that's just go shoom, shoom, it's like sending, let's say you're trying to design chips, so you could then run conventional apps, stuff from Cadence and Synopsys and whatnot, and you can say you can run 1,000 simultaneously or 10,000, and say, okay, given this input, I get this output for the chip. And at a certain point, you can say, okay, you're actually going to know what the chip should look like without using any of the tools. So basically, you should be able to do a digital chip design. You can do chip design. You march up the difficulty curve. You could be able to do CAD. You could use sort of NX or any of the CAD software to design things.
Okay, so you think you start at the simplest tasks and walk your way up the difficulty curve.
So you're saying, look, as a broader objective of having this full digital coworker emulator, you're saying, look, all the revenue maximizing corporations want to do this, XAI being one of them, but we will win because of a secret plan we have. But everybody's trying different things with data, different things with algorithms, and I'm I
like that.
What is
tried
this,
data.
We've tried algorithms.
What else can we do?
It seems like a competitive field, and I'm how are you guys going to win? Is my big question.
I think we see a path to doing it. I think I know the path to do this, because it's kind of the same path that Tesla used to create self-driving. Instead of driving a car, it's driving a computer screen. So it's a self-driving computer, essentially.
Oh, you're saying, is the path just following human behavior and training on vast quantities of human behavior?
But sorry, isn't that? I mean, isn't that training?
I mean, obviously, I'm not going to spell out, most sensitive secrets on a podcast. I need to have at least 3 more Guinnesses for that.
I've got some friends at Jane Street, and they're always talking about how their colleagues are cooking up fun, fiendish puzzles for each other to solve. Well, last week they sent me one. Basically, they trained a neural network, and they gave me the weights of each layer. But they didn't tell me what order those layers went in. And so I had to figure out the correct order using the outputs of the original network. And as soon as I got this puzzle, I went to my roommate, who's an AI researcher, and we both got immediately nerd sniped. Obviously, you can't brute force a solution. The search space here is 10 to the 122 permutations. So clearly, you need some way to reduce the search space. Then my roommate had to go to work, but because I'm a podcaster, I had some time to take a stab at some of the ideas we discussed. And with a combination of simulated annealing and greedy search,